All right, let's do another quick example of a geometric sequence. This is very similar to the example I showed for an arithmetic sequence, where we essentially used like a slope formula to calculate the common difference, and then we're able to get a formula for that arithmetic sequence, which we then use to find the 200th term. So we're going to do something similar here with a geometric sequence. So assuming geometric, right? That's key. Again, we're going to assume we know what type of sequence it is. If we assume it's geometric, if we know our first term, A1, is 81, and we know our fourth term, A4, is 16, then I'm going to kind of graph this out, not graph, but I'm going to kind of write this out like I did in the other example. These are first four sequence terms. The first one's 81, the fourth one is 16. We've got to get here by multiplying by the ratio, times r, and then times r, and then one more times r. So what we're doing is we're going to get from 81 to 16 by multiplying by r 3 times. So I can set up a formula for, or I can set up an equation for this. 16 should be the result of taking 81 and multiplying by r 3 times, times r, times r, times r. This means 16 is 81r cubed. So we can do 16 over 81 should be r cubed. We take the division of 16 divided by 81, that's r cubed, and we can solve for r by taking the cube root of 16 over 81. And the cube root of 16 over 81 can be found by, well, that could be, hang on, let's, 16 is 8 times 2, so the cube root of 8 is 2, so we have 2 times the cube root of another 2 in the numerator. And then 81, is 81 is already something cubed, isn't it? No, 81 is 9 squared. No, that's not the cube root of anything. Hang on. Yeah, it's 3 times the cube root of 3. So that's our ratio. It's not a very satisfying ratio, but that's what it is. That's r. R equals that. So if we want to know an explicit formula for this, all we need to do is use the formula an equals ar to the n minus 1. And so we'll use our first term. An is going to be 81, the first term, and then multiplied by our common ratio, 2 cube root of 2 over 3 cube root of 3. And then raise that to the power n minus 1. So now if we want to know A20, all we have to do is stick 20 in there. So now I'm going to go ahead and use the calculator for this. So I'm going to write 81 times, and then in my numerator, I'm going to put another parentheses to put around my numerator. 2 times the cube root, hang on, math cube root is over here. 2 times the cube root of 2, close the parentheses, and then divide by, open parentheses again. By the way, you need to open the parentheses every time you're going to put a denominator. 3 times the cube root of 3. Okay, and close the parentheses. If I didn't put the parentheses around the denominator, I'd be in trouble. Actually, the parentheses around the numerator are not necessary, but the ones around the denominator are necessary to override the order of operations. Otherwise, the division by 3 will be evaluated first before the multiplication by the cube root, and then the cube root will actually end up in the numerator, the cube root of 3. Which is not what we wanted. So there's our entire r value, and then we'll raise to a power, and again I'll do parentheses, and do 20 minus 1. So I could have just written 19, I guess. But there's the formula, and that gives me approximately, this is a very, very small number, this gives me approximately 0.0028. Now we'll leave it at that. So that's A20. And there we go. So now we can calculate, using this formula, any sequence term we want. This problem is interesting because this is a situation where the sequence is decreasing. We have a decreasing sequence, and that's kind of cute. If you so it's not going down, it's not going up, it's going down. If you look at the actual value of r, let me pull this back again, and let's get rid of some of this junk here. Get rid of this exponent. I just want to do, and let's get rid of the 81 in the front. Okay, so 2 times the cube root of 2 divided by 3 times the cube root of 3. That's 0.58 approximately, right? It's an irrational number. But what we have here is a situation where r is about 0.58, which is less than 1. This means that the sequence is decreasing. Just like when you have an exponential function, if you have an exponential function with a base less than 1, remember, if you're looking at a to the x, y equals a to the x, if a is less than, if 0 is less than a is less than 1, if it's between 0 and 1, then you have a decreasing, like exponential decay situation. So that's what's going on. Basically, it's like exponential decay, all right? And this sequence term is going down from 81 to 16. Okay, I think that's all I wanted to say about this. I'm pointing out this idea that with a r value that's less than 1, it decreases, because in the next section in 13.4, we're gonna distinguish between geometric sequences that are increasing versus geometric sequences that are decreasing, and that makes a big difference in the result when you add them up. So, next section, we're going to talk about series and adding up an infinite number of numbers.